So we want to continue looking at our unit circle a little bit, and I want to examine a couple of things related to our sine and cosine and that before we get into more identities. I told you we were going to learn a number of different identities. We've already learned the reciprocal identities. We already learned that tangent equals sine divided by cosine. Alright? Before we get into a couple of the other ones though, I want to just give you a preliminary look at our sine curve and talk about a couple of terms here that relate to them that'll make at least one of the other identities make a little more sense, okay? We will revisit graphing and spend a good amount of time graphing these and also making models by hand in the upcoming days. All right? So let's take a quick look and think about our unit circle here and come up with what this is here. All right, we're looking at the graph of sine of x, okay? Y equals sine of x. So x is the angle, y is the value of sine. And you'll notice here, just looking at these points 1, 0, 0, 1, negative 1, 0, and 0, negative 1, we actually can come up with the shape of our graph, okay? Just as a matter of review, which coordinate was the sine of the angle? Was it the x or the y?
X.
I got a 50-50 shot.
Yeah, 50-50 shot. Come on, take a risk.
X.
No, Y.
It's y, okay? It's y. All right? And look at our unit circle. Here, y is the opposite side from our angle. Y over 1 is sine. So our angle here is the y coordinate on the unit circle is the value of sine for each angle. So what's the sine of a 0-degree angle?
0.
0. Okay, it's 0. All right, that's why we have this point right here at the origin. What is the sine of pi over 2? It's 1. Okay? And notice, by the way, sine never goes higher than 1. Okay? Which, if you think about it according to the right triangle, that makes sense, right?
So these radians, like the markings, each one is a pi radian, like a 1 pi of radian, a pi radian. Oh my god.
In this case, yeah, we have pi. This would be 2 pi, 3 pi, and 4 pi. That is true. Okay. But hear what I was saying there. The value of sine will never be greater than 1. If you think about it in terms of the right triangle, sine is opposite over hypotenuse. If the hypotenuse is always the longest side, then the denominator will always be bigger than the numerator, meaning you're never going to have anything bigger than 1. Okay? So, we have here 0, 0. Then at pi over 2, sine of pi over 2 is 1. Sine of pi is 0. Okay, so we have that point. Then sine of 3 pi over 2 is negative 1. Okay, so here's 3 pi over 2, and we're down here at negative 1. And then when we do the full circle back at 2 pi, sine equals 0 again. So if we kept going, and we had, say, 5 pi over 2, the sine there would be 1 again. And then 3 pi, we'd be back at 0. Okay? And then at 7 pi over 2, we'd be back at negative 1. And then once we went around for the second time and got back to the beginning, it would be back at 0 again, at 4 pi. And we could keep going around and around and around and around, both in the positive direction or in the negative direction. And it's going to follow this same wave pattern that you see here. That's why sine and cosine, for that matter, are known as periodic functions. Okay? Yes?
So would the cosine just be the opposite, like the flip of the wave? So it would be like 0, -1, 0, 1, 0, -1.
It's not the flip, but you'll see it's very similar. Okay? We'll look at that one closer later. So we have a couple of terms here. I said this was periodic, and this term period refers to the distance. If it's a distance, that means it's always positive, right?
Yes.
Distances are always positive. So it's a distance that it takes to repeat, or to complete one full cycle, if you will. All right? So in this case here, we start at 0, it ends at 2 pi, and then repeats, and then it takes another 2 pi to repeat. So we would say the period, we often use capital P, the period is 2 pi, because that's the distance it takes on the x-axis for it to repeat. Okay? The amplitude is a little bit different, okay? Amplitude is half the distance between the max value and the min value, okay? So here we have the max value at 1, and we have this min value at -1. So the distance there is 2. Half of that is going to be 1. So our amplitude is 1. And that's something you need to just get comfortable with and know. The period is 2 pi, the amplitude's 1. Unless we transform it somehow. And by the way, we are going to work a lot with transforming this graph. Okay? Now, I want to develop the first of our next set of identities. Okay? We're learning the fundamental identities. We already learned the reciprocal identities. We already learned that tangent equals sine over cosine, which, by the way, that also means that cotangent is
cosecant over secant. Yeah.
technically yes, but that's not typically how we do it.
What?
That actually does work, but think about it. If tangent is sine over cosine,
Yeah.
then cotangent would be
cosine over sine.
cosine over sine. All right.
Okay, yeah, makes sense. No, you know, I get it.
So actually, no, it would have been.
No, it would've been
No,
that,
you were
because
right.
the
Yeah,
opposite
cosecant over
reciprocal.
secant.
You just
We
think
just don't normally do it that way.
it.
All right, so let's look at our next set, and these are what are known as the Pythagorean identities. Okay? Now, question, how do you think we're going to develop the Pythagorean identities?
Pythagorean.
The Pythagorean theorem, okay? This is why they're called the Pythagorean identities. Now, you'll notice here I have the first quadrant from my unit circle again, right? And just as a reminder here, okay, the points on the unit circle, the x and y coordinates were what? What was the x coordinate in relation to theta? Cosine, all right? It's the cosine of theta. And then the y coordinate is sine of theta. I know I'm repeating myself a lot, but I want this to really get into your head. Okay? So let me label the sides of the triangle and see if you can't come up with the identity yourself. This would be cosine of theta. This would be sine of theta. So what equation could I write?
Cosine squared plus sine squared equals
Robots.
1?
Yes.
Oh.
Okay? You know, let me erase it and write it better. Okay? Sine squared plus the cosine squared of theta equals 1. Okay? if you try that out with your unit circle, it'll work. Okay? Think about 30 degrees. Or let's do radians, pi over 6. Okay? Sine of pi over 6 squared plus cosine of pi over 6 squared. What's sine of pi over 6? That's sine of pi over 4.
Pi over 3.
30 degrees?
Well, that is pi over 6 is 30 degrees. What's the sine?
Half.
A half. Okay? So 1/2 squared. What's the cosine of pi over 6?
2 squared.
Good. Root 3 over 2. So root 3 over 2 squared, this is where your unit circle's coming in.
Yeah.
That's why we've got to know that. Alright, so what's a half squared?
1/4.
1/4, good. What's the square root of 3 over 2 squared?
3 over 4.
3 over 4. What's 1/4 plus 3/4?
Oh my
1. Da 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 da. Okay? It works. Now it works for that one. What we did actually proves that it works no matter what the angle is. Okay? But I just wanted to illustrate it with something that we knew from our unit circle.
Wow.
Okay? Now, there are 2 other Pythagorean identities. Okay? I'm going to show you how to derive them. Okay? Because honestly, half the time I don't remember exactly what they are, so I just rederive them in my head. It's that easy. Okay? So, first one, I'm going to divide everything by sine squared. If I do that, I've got to do this one, and I've got to divide this one. Okay? So sine squared over sine squared is? 1. What's cosine squared over sine squared?
Tangent squared theta.
What is it?
Tangent theta. Theta.
Cotangent. Cotangent squared theta. Sine over cosine was tangent, so cosine over sine would be cotangent. And then what's 1 over sine squared? No? What's 1 over?
Cosecant.
Cosecant.
Whoa.
Cosecant squared theta. So guess what? There's the second of our Pythagorean identities.
Oh boy.
Alright?
Bruh.
How do you think we're going to get the third one?
You do the vice versa, you cosine. Over.
Divide everything by cosine squared. You could do that. Okay? So for our third Pythagorean identity here, check this out. We got the last one by dividing everything by sine squared. So we're going to get this one by, what do you think?
By dividing by cosine squared.
Yeah, divide everything by cosine squared.
Yippity-doo. I don't have any more room for this.
Okay? So if I do that, what's sine squared over cosine squared equal? Very good. Tangent squared. Okay? Cosine squared over cosine squared, of course, is 1. And then what is 1 over cosine squared? Secant squared. Okay? And guess what? That's our third one. Okay? So there are 3 different Pythagorean identities that we can use. And we can use them in a variety of ways. Okay? Now, in the future, particularly for this, we're going to be doing this a lot next units. But I just want to show you so that you can kind of see where we're headed with some of this. In the future, we will be solving equations. And for example, this equation right here, we can't solve because we have a cosine and we've got a sine in it.
It looks like a parabola.
Well, actually, this is a quadratic equation. However, I still can't solve it until I have all one trig function. So what I would do in this case, I'm going to take that sine squared plus cosine squared equals 1. And I want to replace sine squared with something. What could I replace it with?
Cosine, or, what's it called?
Cosecant.
Cosecant. That's
Or
what
no,
it-
No, it's not a 1 over.
So it can be.
Think about what we're looking at here.
1 minus.
Oh, an A squared. Oh.
1 minus, good. 1 minus sine squared is 1 minus cosine squared. So guess what? If I plug that in here,
oh, then.
3 times 1 minus cosine squared theta, now I have an equation that only has cosines in it, and I can use the quadratic formula to figure out what cosine of theta would equal. And then I'd have to use the inverse cosine to figure out what theta actually equaled. Alright, but here we have a quadratic form. But we can't do anything until we use this identity first to get the equation into all cosines. Alright?
I feel like we're like when we do this, we're gonna be like we're gonna forget all about like the entire thing.
No, you won't. We'll be doing it so much you'll be good. Alright?
But by extension, cosine also equals 1 minus sine squared. I mean, cosine squared also equals 1 minus sine squared, right?
That's correct. So if these were switched, if it were a cosine squared minus 5 sine, then yeah, we would want to plug in the 1 minus sine squared for cosine squared. Or if it were a secant squared minus 5 tangent theta, we would want to say, oh look, secant squared is tangent squared plus 1, so I could throw a tangent squared plus 1 in there. Now everything's in terms of tangents. So depending on the equation and what trig functions are already there, this is why we're learning all these different identities. Because there are going to be equations that you've got to use these identities with in order to solve them. Okay? So, alright. Now, this next page here, you may even want to take a screenshot of and paste the picture right in your IP. Because this right here, these are our fundamental trig identities. And you should know them by name, not just seeing them and knowing what they are. But if I'm talking about the quotient identities, you should know that I'm talking about tangent equals sine over cosine, and cotangent is cosine over sine. If I tell you to use one of the Pythagorean identities, you should know what I'm talking about.
Did we go over these?
Okay.
Did we go over these two or are we gonna
We just did that,
Okay.
right?
Yeah, sure.
Yeah, we just did
I
those.
remember seeing the first one. I don't know the other two.
Well, we developed the other two, right? We divided by
Yeah.
cosine.
Oh
and
my god. Oh,
yeah, there we
there
go.
There we go.
Okay.
I scared you, didn't
I knew you were awake. So, alright, so you've got those. I want to look at one other set of identities here, though. They aren't technically one of the fundamental trig identities, but they are ones that we use quite a bit. And those are the cofunction identities. Okay? The cofunction identities. Someone asked, I don't even know if it was in this section earlier, that how come sine is paired with cosecant and cosine is paired with secant? The only one that seems to make sense is tangents paired with cotangent, okay?
One co per pair.
With this, you're right, 1 co per pair, that's good to remember. With this, the cofunction identities are called the cofunction identities because these ones really make sense in the way they're paired up. Sine and cosine are going to be paired together. Secant and cosecant are paired together. And tangent and cotangent are paired together. Okay? Now, let's look at what the relationship is. And at least with sine and cosine, we'll see kind of where it comes from. It'll extend to the other pairs as well, but we're not going to develop all those. Alright, so check this out. if you look at the first quadrant of our unit circle, you see that, the coordinates kind of repeat each other. All right, and you see also here, here's a root 3 over 2, here's a root 3 over 2. Here's a 1/2, here's a 1/2. And obviously root 2 over 2 is repeated within the same point there. Okay? But if you think about what these actually are, that will actually give us the cofunction identities. 1/2 here at the 60 degrees, or the pi over 3. Now I'm going to use degrees for right now just so it's easier for us to recognize. That 1/2 is the what of 60 degrees?
Well, it's your y, so in your
No,
y.
it's
Oh,
the...
it's the x,
It's the x.
cosine, my bad.
Alright, so that's the cosine of 60 degrees is 1/2. Here's the other half. What does that equal?
It's a sine.
The sine of 30 degrees.
Oh, so it's just proving why it works?
Yeah. Okay? We could go through all of these. This root 3 over 2 up here at the 60 is the what of 60?
The sine.
Sine of 60. Alright, sine of 60 degrees is root 3 over 2. Well, down here, root 3 over 2 is the what of 30?
Cosine.
The cosine of 30. Okay? And even here, the sine of 45 equals the cosine of 45. Alright? Now, you'll notice here, I have that all written over here. You'll notice 30 and 60, 60 and 30, 45 and 45, those pairs of angles all add up to 90. Okay? We're dealing with complementary angles. Okay? Complementary angles. Angles that add up to 90. So the cofunction identities are identities for when we have trig functions of two different angles, but those angles add up to 90, or if we're in radians, pi over 2. Okay? And you see here the relationship. Sine of theta equals cosine of pi over 2 minus theta, or 90 minus theta. Secant of theta will equal the cosecant of pi over 2 minus theta. And tangent of theta equals the cotangent of pi over 2 minus theta. Now, I've only written one set of these, but they also apply written in the reverse order. Cosine of theta equals the sine of pi over 2 minus theta. And cosecant theta equals the secant of pi over 2 minus theta. And of course, cotangent theta equals the tangent of pi over 2 minus theta. Okay? Make sense? Alright, now, we're going to use these identities in a lot of different ways. Okay? We will use them eventually to solve equations. One of the things we'll be doing in this unit is some proofs. Next unit we're going to do a whole lot more proofs. Okay? But in this unit we're going to look at a few proofs. And I want to point this out. A couple of the applications so far that we have. Here's one. One of these is on your actual required IP, but here's some extra practice for those of you guys who like extra practice. If I'm looking at these, the sine of 60 and cosine of 60, I could use a quotient identity to find tangent of 60. Because tangent of 60 is sine of 60 over cosine of 60. So that would be root 3 over 2 over a half, which is just root 3. Okay? However, notice not all of them have a 60-degree angle. Part B has a sine of a 30-degree angle. Well, sine of 30 is sine of 90 minus how much?
60.
60. So good, that's the same as cosine of 60. See how we can use these identities?
Yeah.
What's the cosine of 60? It's a half. Now, you should know sine of 30 anyways, it's from the unit circle. But just to show you how we could use these identities. Alright? Now, this is another one, it's a little less obvious what you're supposed to do, okay? So I want to do one of these here with you. Alright, check this out. You're supposed to use identities to show that the one side equals the other. I would recommend that you start with the more complicated looking side and try to make it look like the simpler side. You can also do something with both sides and kind of meet in the middle, you know? As long as you end up with the two sides equaling each other, that's what matters, because then you've proven that they're equal. Alright? So, for example, on number 49, if I want to prove that tangent times cotangent is 1, I would use, well no, this is the thing, with these, you do not use algebra.
Okay.
You don't take things from one side to the other, because we're not going to assume that they're actually equal. But what I will do is I'll say, okay, well I know that tangent of theta times cotangent is 1 over tangent, right? Well, so if I have tangent times 1 over tangent, that's tangent over tangent, which is 1, okay? Now that was a relatively simple one, but maybe I have 53, okay? On the left-hand side there I see two binomials, alright?
Why not or no?
I could multiply those out. What would I get if I multiply those out?
Cosine squared
Minus
theta
1.
plus 1.
Hang on. We'd get a 1. We'd get a 1.
Yeah.
Minus cosine squared.
There we go. Minus cosine squared. Those are conjugates, right? The outers and inners cancel each other out. So, minus cosine plus cosine cancels out to 0. So I just have 1 minus cosine squared. Alright, well, using my Pythagorean identity, I could say that cosine squared equals
1 minus cosine.
1 minus...
Tangent. 1 minus. Wait, sine equals?
No, cosine squared equals...
Can we just say cosine squared equals
1 minus sine.
You could. I'm just taking this kind of a little bit more roundabout way, but... Alright, cosine squared using our Pythagorean identity is 1 minus sine squared, right? So, that's 1 minus 1 is 0. Negative
Times the negative.
times the negative would be a positive sine squared. So, we just proved it's equal. Okay? So that's what you're going to do. Some of them are very simple, some of them are a little more complex.
Why do you have to prove the right side? Like,
That's the whole point of the problem, is we have something here, we want to prove that this equals this.
okay.
Really what we ought to do here is think of it like this. Every one of these, put a little question mark above the equal sign. Is it actually equal? The point of this problem is to determine whether or not they are actually equal. Okay? Now the other two of these I know are on your required IP, so I left those for you to try. Okay? So, I'm gonna let you guys work on some of this here the remainder of the time, and that'll be it.